So welcome to this review lecture of MCS 472. We are about in the middle of the course. And today we will be reviewing for the midterm exam. So the lecture consists of the policy for the midterm exam and then also 6 representative questions. So the review is not complete. I will repeat this a couple of times. Please review also the homework exercises. Okay, so the midterm exam will happen this Monday. It will be an online exam, so I will email out the questions shortly before noon. And there are two options. Either you submit by 1 o'clock at the very latest, but prepare to submit 10 minutes before 1 o'clock. You upload one Jupyter notebook on to Gradescope. The second option is that you will submit later, but then you don't get exam credit. But then doing the questions will still give you homework credit. The third option actually is doing nothing, but then more weight will be placed on your final exam. So there are three options: doing the exam on time as a regular exam. The exam is open book, open notes, and you will have to reply in a Jupyter notebook. The second option is then not to hand in, but to hand in on Wednesday before noon. Then you will still receive homework credit for this. But also in that case, your final exam will be weighted for more. So the third option, doing nothing, means that you do not get that extra homework credit. Okay, so here is the list of topics. So it covers the what we have covered until the first 19 lectures, so minus the week on project presentations. So I do not have any specific questions prepared on Z transforms and on Fourier transforms. So note that there might be some problems there. Also, regression is actually not really covered. So I have only time for 6 problems. So I will try to explain in greater detail what is expected of you solving those 6 problems. The exam will also be of that same size, 5 or 6 problems. Most likely 5 problems, so in an exam of 50 minutes, I would expect that you can do the problems in and about 10 minutes. Okay, so here is the first question. So we have two types of medicine. The first medicine costs $1 and is effective in 80% of the cases. If it's not effective, then actually you will have to go to the doctor, and that costs you $10. So in the 20% of the cases, you will have to go to the doctor. So there is an expected loss there. Now there is a new drug out there, and that has a much higher rate of success. However, it also costs twice as much. So is it justified from a financial perspective? So if you want to be sure about your health, you indeed goes for the more expensive medicine. So the first question asks, is the $2 justified? And the second question is a variation on this. If we have justified it, could actually a higher, or if we didn't feel it was worth it, what would be the fair price for the new medicine? Okay, so we have computed expected loss. So in some sense, what is the incurred loss of this? So you will have to spend $1 in 80% of the cases. That will be your loss, but you will be cured, so you will have gain. In the other 20% of the cases, you will have to go to the doctor. So you have bought the medicine, but then there is an additional cost of $10 for the visit. So for the first medicine, your loss is $3, the expected loss. For the new medicine, you will have to pay more. In 95% of the cases, that will do it, but in the remaining 5%, you will have to incur a higher loss of $12, but that sums up to an expected loss of $2.50. So, what's the conclusion of this? So the price of $2 is twice as expensive, but much more effective. That is actually a better choice. Okay, so one could also consider this now from the viewpoint of the manufacturer of the new medicine. So here you see all the data again. So suppose that so $2 was a good price. So for $2 you buy the new medicine. But how high can you go? Well, it turns out that you can go as high as $2.50. Now, why is that? Because the first medicine has an expected loss of $3. And now you compute the expected loss with a variable. So we don't know what is the same price, what is the price that would give the same expected loss. So let's compute it. So we have a simple linear equation, and it turns out that the difference is 50 cents. So that means that for $2.50 we have the break even, but of course when things break even, we don't really like to have the extra visit to the doctor's office, so we will take the new medicine. Otherwise, if the price is higher than $2.50, we will not buy the new medicine. Okay, that's our first question. So I said that we did the Takeuchi quality control, but with Takeuchi quality control, you quantify the variation of the target. So here the target was a reduction of the fever, and quantify the loss if the drug misses that target. Okay, so now simulations and lifespan. So there is a race, 1,000 miles. Now the race imposes kind of excessive. The race is kind of excessive, and imposes stress on the tires. So under those circumstances, tires only last for 600 miles, and the standard deviation is 200 miles. So we considering the case where we start with 4 new tires mounted, and there are 4 spare tires. Now, given the expected lifespan of the tires, what are the odds of finishing this race with the 4 mounted tires and the 4 spare tires? So let's set up a simulation to decide those odds. And we will run the simulation 10,000 times to get an idea for the probability. So in some sense, 600 miles, you would do 600 and for the first set of tires and 600 for the second set of tires. It makes actually, it might not be such a bad idea. Okay, so here is the simulation. It's coded up in a Julia function. The main parameter is the number of simulations. So you could actually focus on the inner loop here, on the first body here. What do we do? In every run, we draw random numbers, normally distributed. So the standard function, the rand n, gives us a normally distribution with average 0, so we add 600 to this, and standard deviation is 1, so we multiply the random number by 200. So that will give us, for the 8 tires, that will give us 8 tires with kind of a random selection of the lifespan. So we start with the first tires, and then we can, as far as the race goes, the race is not over if we can change tires. So we will sort the tires and move always the smallest tire with the smallest lifespan. We exchange it, and we do this. We can do this 4 times. So we replace the tire with the shortest lifespan by the other tire. And then we check the minimum of the lifespan. And if so, actually, what happens is that the lifespan of the smallest tire actually gets added to. So it is as if we take the shortest lifespan and we add the lifespan of the spare tire to this. So this simulation takes into account the replacement of the tires, and also the fact that we actually need 4 tires that have at least a lifespan of 1000. So each time when this happens, we count a success. And this simulation function, when it runs, it actually returns the total number of successes. So we're going to run this for 10,000 times. If it always works, then we will get the number 10,000 back. But we will see the percentage of failures in this total simulation. So that will give us the estimate for the odds of finishing the race in time. So here is the result of the run, and that gives 3,700 and something. So if one runs this, the average, sometimes you may see 3,800, sometimes 3,600. So the probability is about 37% that you can finish the race with your 4 tires mounted and with your 4 extra spare tires. So the odds are actually lower than what we would have expected with the 8 times the 600. So not realizing fully that we need a full set of 4 tires that actually make the 10,000. Taking into account the swapping of the tires. So in a way, this simulation also simulates the process of doing the race. Okay, so we solve a recursion. So here, let's look at this problem. We start with an empty savings account. So each time $400 is deposited into the account, then 20% of the balance of the savings is withdrawn at the first day of every month. So let's set up the recursion relation, solve the recursion relation, and with this scheme, so we take 20% of the 400 deposited out. Will we ever actually get rich? So is there actually a limit to the balance if we keep on doing that? Okay, so here is the setting up of the recursion. So the balance is each time augmented with 400, but the balance, so to the 400 we add 80% of the balance of the last cycle. And we start with 0. So this translates the evolution where we look at every month, starting at 0. So we have used all the data. So the 20% needs to be reverted into the 80%. Okay, so we can solve this recursion by plain substitution because it's a recursion that has only one term. So let's do this. So we observe the pattern. So if we replace the 0.8 by 4/5, so we see that after doing the substitution once, we get 4/5 to the power 2. And we get the 400, but the 400 is multiplied also with this 4/5. So if you have difficulty seeing this now, let's do this another time. So you will see 4/5, so the bn minus 2 is replaced by 4/5. So then if you factor things out, if you collect the terms, or perhaps if you want to see this better, take n equals 2. At n equals 2, we are at the base case, and then we have the n, if we collect the terms, we have 4/5 to the power 2. So we can get at the base case if the n, we have to do this n times. So starting at n equals 2 gives the power 2. So for the other term in the summation, so we have the monthly deposit, the sum 400, gets multiplied by 4/5 each time, but also with a power. And the power is 1 less than what the balance gets multiplied with. But there is a summation here. So what we have found is an explicit formula for the balance, where actually we can forget about the first term because we start with an empty savings account. So we have to use now the sum for the geometric sum. So we have the explicit formula. The explicit formula can be rewritten, so we have 4/5 minus 1 in the denominator. That means that we have minus 1/5, which means that we're going to multiply the 400 by 5. That gives us the 2000, actually minus 2000, but we will flip the sign of the numerator. So the final result, we write 1 minus 4/5 to the power n. Well, will we ever get rich? Probably not. So, well, it depends on $2,000. It's a lot of money, but it's not exactly being rich. So there is an upper bound to this scheme. So we will, on our savings account, if we keep on doing that, withdrawing 20%, we will never get more than $2,000. Okay, so we are making progress. I have solved half of the questions that I prepared in about half of the allotted time. So let's look at a linear programming problem. Um, Perhaps that can take a little bit more time. So what do we have? So we have to advise a rental company that must order new boats. So there are three types of boats. We have the one-seaters, the two-seaters, and the three-seaters. Now the boats get larger, so they require more storage to store. They're also getting a little bit more expensive. Um, so we have a cost there. We also have a rental price. So the um, boats that are of higher capacity, we can rent at a higher price. But knowing a little bit the needs of our clientele, if you have two people coming in, sometimes they want not to share the boat, so you have to turn them away. So they would rather have each their own boat. So there is a higher need for one seat boat types and lesser need for two seats and also lesser need for three seats. Okay, so we can actually write this table as saying that for every type of boat we have some constraints on the storage and the cost to purchase, and for every boat there is also a gain that can be gained by this. So if we didn't have the constraints on the needs, then we would only, and no constraints on storage, we would probably buy only boats of type 3 because they are most profitable. But they're most expensive as well. So we have only 400 square feet in our storage. So if we have to, at the end of the day, if we have to store or lock away our boats, so we don't want to leave any boats out unattended. It could also be that we have a limited K. So if our shore capacity is limited, what we can oversee as well. And of course, there are always budget limitations. So under these constraints, so we have the storage constraints, which are the upper limits, and then we have the lower bound on the needs for each type of boat. How many boats of each type should we order? Okay, so the solution is here presented right away. So it's a maximum problem. We want to maximize the rental revenue that we can get. Well, first of all, we need to decide on the variables. So what is the problem actually? We need to decide on the number of boats of each type. This is actually an integer problem, but it will turn out that we can solve this with linear programming with continuous variables. So x1, x2, x3 will be the number of boats of each type, and we will, if there are fractions, we will round down. Or perhaps round up if we can afford it with the storage and the constraints. So we have the storage constraints for which we use the numbers from the storage area column. So the 2 multiplied with the number of boats of type 1, 3 the number of boats of type 2, and 4 the number of boats of type 3. So this added up will, the left hand side of this first inequality will determine here what is the storage that will be occupied by our boats. Shouldn't be more than 400. We do the same for the cost. So we have a limited budget of $10,000, and we have the total amount that is spent on boats of type 1. We multiply this with the cost per boat, the 122. Then we multiply the x2 with the respective cost, and also x3 by the 150. These are our first two constraints, and these are over of the type less than or equal. Then we have the needs for the boats, 20, 15, and 10. And normally all our variables are positive, but here we have lower bounds. So this is a three-dimensional problem. How do we solve this? We can probably try to solve this by hand, adding slack variables and then replacing the zero values with the ones that have the most profit. So we will essentially, when we work with three slack variables, we will bring in first the type 3 boat, because that boat gives the most profit. But we will run into one of these two constraints here. Alright, we don't really solve things by hand in this course. This is a computational course. And there is the very convenient optimization package in Julia, which allows us to work quite in general. So we have we can store the data types in a data frame that allows us to oversee. So the table that we have, which consisted of 15 integer numbers, we can represent that data. We could do this in a matrix, but actually with the data frame, we can label every column. So the first column was the type of each boat. Then we have the area that each boat occupies, its cost, then the rental price, which will determine our revenue, and then we have the need for each boat. What is not yet in this data are... No, actually everything is in this data. So when we solved the diet problem, we did not have, we had limits separately, but here everything is in one table. Very convenient. Alright, we will use the GLPK package for our linear programming problem. So we make an instance of a model. We declare the variables of our model. Now here we work only with three variables, but see, this is already very useful. We can just select from the variables the type. So the variable names will be 1, 2, 3, corresponding to the 1, 2, 3 types. The objective is a maximum. So we will maximize the rental price times every type of boat. And the data frame was called boats. So for every row in that data frame, we will sum up. And that will define the objective that we reformulated earlier when we solved this, when we set up the model. Okay, so then we had two constraints. So we had the constraint on the storage and a constraint on the budget. So these are two expressions that we're going to add to the model as constraints. Okay, I said that the model was, the table was self-contained. I was not correct. So we have the constants 400 and 10,000. 400 is the capacity of our storage area, and $10,000 is our budget. But you see that in both cases, adding one extra constraint is actually not difficult. So we run over the columns area and costs. So here we have two constraints on the area and the cost. So if one had, so this works for any number type of boats, so it scales over there. If you would have a linear problem, a linear programming model that would have many columns, then we could have an outer loop that would run over the columns of the data frame, or over a specific range of columns in the data frame. So this modeling language is quite convenient. So then we have more constraints determined by the need. So that was the last column in our data frame. So for each boat, we add a constraint. So here you see an example of where we are adding constraints after the other. So printing this model is necessary to verify that everything actually went fine. So there is a Jupyter notebook that is posted. So let's now optimize it. So let's now solve it. So the problem has a feasible solution. So here we see the summary. So, and the solution that is returned is optimal. Okay, so let us look at the solution. So here it is. It corresponds to this objective that was delivered. And here we see the values. You see that there are fractions. So we will have to round down in our last type of boat. So in some sense, the constraints on the needs were integers. So we knowing that with this round down, we will not violate the constraints on the needs. So if it works for 37.4, it will also work if we round down. By rounding down, we will not violate the other constraints either. So it's only that our profit, our objective value will drop a little bit. Okay, so that's another problem solved. Now we have still two problems, for which I still have 20 minutes time, but I don't think I will not even need 15 minutes. So, a cost-benefit analysis. We have an investment that we make today. So today we have to come up with $10,000, and that will save us $1,500 each year for the coming 8 years. So the bottom line question is that, is it worthwhile? Well, if you would multiply 8 times 1,500, you would think yes, because it will save us $12,000 in total. So we would have, at the end of the 8 years, we will have $2,000 more. However, this was not really using the discount rate of 6%. So the investment has to be paid now, so that's the sacrifice that we make. So our first costs, and the $1,500, that is savings. That's a sum of money that we will get only after the first year. So the $1,500 should not be counted as a $1,500 of today. So we have to compute the present value of the future savings, and that can be done with a simple computation. So this is the inverse interest computation, where instead of using a positive interest rate, or here the discount rate, we use the negative rate. So we have the minus R, and we run this for 8 years. So the sum, the t in the sum starts at 1 and then runs through 8. And we apply, so there's each time the same saving, we each time apply the continuous compounding. And we sum things up. So it could have been worthwhile to see whether we would ever get there, but actually we do not break even yet. So the present value is less than 10,000 of our future savings. So it's 9,200. So related questions here would be, what would be the return on investment? So what would be the rate, the discount rate for which we break even? For that you will need to set up a nonlinear equation and solve that equation for R. The alternative question could also have been, if we had a much lower discount rate, say only 3%, then it might very well have been possible that this investment was worthwhile. And then it's a good question is, what is the payback period? So you can actually then see how many years do you have to wait till you have recovered your investment. Okay, so that was a short question. Okay, so now to our last question. So we consider a market with two simple demand and supply functions. So demand goes down when the price goes up. So you see here this hyperbolic. So demand, so when the price is zero, the demand for the quantity will be infinite, which is actually not so realistic. But it will work around, the model works around the equilibrium price. So the supply function goes up. So compute the equilibrium price and the revenue for this problem. Now we consider that the government wants to help the producer, wants to increase the supply, so, and provides a subsidy of $1 per item. Now this will increase the supply. This will also benefit will increase the supply, so this will lead to a new equilibrium price. It will benefit the producer. So in some sense, one can always ask with this, if the government actually provides this subsidy, is that not giving away money for free to the producer? But there is also a benefit to the consumer. So the equilibrium price, as we will see, will actually go down. And the consumer will also benefit from this. So it might even be that the percentage-wise, that the consumer benefits more. Okay, so here is the first solution. So we will have to solve a nonlinear equation. So actually it's a cubic equation. If you multiply out P, then we see that the equilibrium price before the subsidy is $3.32. The revenue is the price multiplied with what the producer is willing to supply at this. So we take the supply function, or we can actually also take the demand function. It doesn't really matter. So we multiply the quantities with the item solved. So this gives us the revenue. Okay, so the units here don't really matter much. Okay, so now we have the main difficulty. How do we compute the new equilibrium for the added subsidy? So what happens when the subsidy comes in? Well, the supply function will increase. So the producer receives $1 more per item. So now the producer has an incentive to start producing more. So there is a new supply function. And redoing all the computations, it means that the equilibrium price actually drops. It was $3 something, so now it becomes $2. There's also more supply, and the revenue is actually increased as well. So we compute with this new equilibrium price, we redo all the computations. So the difficulty in this exercise is to rescale the model. So knowing that this has an effect on the producer, and the supply function is therefore affected, not the demand function. So in some sense, it seems that this change would only benefit or would only affect the producer. But with the new equilibrium, this is not the case. Okay, and there is an error here. So this is my last slide. I still have to fix this then. So if we consider the difference between the equilibrium prices, so the equilibrium price dropped by 85 cents. So actually the consumer gets to benefit 85 cents. And 85 minus $1 is not 25, but it is 15 cents. So of this subsidy that goes in its entirety to the producer in the end actually only gets about 15 cents of this. The main beneficiary of this subsidy is actually the producer, is actually the consumer. Okay, I should probably have prepared more problems, but on the other hand, the size of the review should kind of be indicative for the size of the exam. So in reviewing for the exam, look at this at the review problems, and also look at the homework problems. So I did not have problems specific for transfer functions and filter design and the fast Fourier transform. Please also in the homework consider those problems. Okay, I hope that this recording is useful.